Okay, so taking a look at finding the area under the curve. So area under a function. What do we have? Well, here's the curve. The area under is, of course, in here. That makes sense, but since we're going from 0 to 5, we've got to include this area over here. Now, when we've looked at this before, again, area under is always with respect to the x-axis. So when you think under, you may think all the way just to the x-axis. So, but this is nice because the area under the curve is just the definite integral from 0 to 5 of the functions of 4x minus x squared dx. Again, your heights times your base, and now just find the definite integral. So that's 2x squared minus 1/3 x to the third from 0 to 5. And plug it in. So 2 5 squared minus 1/3 5 cubed minus 2 0 squared 1/3 0 cubed. And when you do the calculation, you get 25 over 3. 50, which is 125 thirds. Okay. Now, same thing here. Area under curve doesn't matter from here, from x equals 0 to x equal 1. So this is the area we are looking at. In here and here. Well, again, because what it says, area under the curve, it's just a definite integral from 0 to 1 of 2 cosine pi x dx. Okay. So 2 times 1 over pi sine pi x from 0 to 1. Now, some of you may go, wait. Where's the 1 over pi coming from? If we use the u substitution, pi x for the angle du, so 1 over pi du is dx. Now, you can do the substitution, but I'm hoping by now we've done enough that if you have a constant times the variable, when you do that substitution, you're going to be dividing by that constant each time. Now, if it's already there, if this was pi instead of 2, I'd have the pi dx and be done. So you don't need the substitution. Let's put it this way. I don't require it. You may need this for yourself, but I don't require that if you can see that. So again, plug it in. But I'm going to go ahead and factor that constant of 2 over pi. So when I substitute in, I get sine of pi times 1 minus sine of pi times 0 well, the sine of pi sine of 0, I know, looks strange. How can you get area if you actually have area? Well, think about it again. This is positive area because it's actually physically under the curve. And how about this? That's not under the curve. It's actually over, or the negative under. Again, that's because it's below the x-axis, ding, 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 it's a negative area. When we look at the terminology, when we look at it as the area under a function. Slightly different this time. We're going to enclose the area. So what is the area enclosed? Same graph. So we've got this positive area here. Okay. And then this negative area down here. Well, if we want to count that negative area, not as a negative number, but as area, as an absolute value, what can we do to that? Okay, now we just can't go from 0 to 5 anymore because that's what we did before. That's the area under. So we've got to break this apart. Well, what is that x point right there? So what is the area where the function is positive area? So what's that area? I'll call it A1. Well, how do we find that point? Well, where's the function? Equal to 0. That's all, because that's on the x-axis. Ah, 0 and 4. That's nice. So this first area is from 0 to 4 of what? 4x minus x squared dx. Now I'm just going to do it in one line here. How about this area down here? Oh, well, let's call it A2. But again, that's going to be from 4 to 5, because we're going up to only up to 5. But we don't want this function again, because that's not under. That's actually over. So we want the opposite of that area. And I'm going to add the 2 up. Now, what could we do with the opposite? We've got a couple of different avenues to take. We could take it out and subtract, or we could distribute. I'm going to distribute that in this time. But I'm going to do that at the same time as my antiderivative. So 2x squared minus 1/3 x cubed from 0 to 4 plus, now again, this is going to be a negative 2x squared and a positive 1/3 x cubed from 4 to 5. And so I just ding ding before I did the antiderivatives. Now be careful with this. Don't do too much of a shortcut. Still substitute. So 2 times 4 squared minus 1/3 4 cubed minus the 0 plus. So that's the first. Now the second. 5 squared plus 1/3 5 cubed minus negative 2 4 squared plus 1/3. So that's your second area. So 16, 32, 64, over 3. That's 0 plus 25 times a negative 2, 125 times a third, minus negative 32, and a positive 64 over 3. So let's see here, we got 32. Let's go ahead and go. So 32 and 32 is 64, minus 50, negative 64 30-seconds, and a negative, so that's 128 over 3, plus 125 over 3. I don't know what that's going on. Okay, so 14 minus 3/3. Get rid of that. Okay. Yeah, so that total area is 13. Now, why didn't we have that before? Because we counted this A2 as a negative. So again, this time it's the area between. So again, positive area, negative area. Yeah, that was bad. So we're going to add that part. So, what's that? So where is 2 cosine of pi x equal to 0? Where is the angle? Oops. Pi x equal to pi over 2, because that's where the cosine is 0. 1/2. So we'll split it up. The first area, since it's already positive, so 0 to 1/2, 2 cosine pi x dx, plus the negative area. Well, we don't want that negative, so let's make it the opposite. Same function. So from 1/2 to 1. Again, closed interval from 0 to 1. And we've already did these antiderivatives, so I'm not going to go back through that. And it's what's nice about this, it's the same antiderivative. This one just has the negative in front, that's all. So, fundamental theorem of calculus, 2 times. Antiderivative, now, upper limit. Actually, we'll just do that. And then sine of pi times 1/2 minus sine of pi times 0 plus a negative sine of 1 times pi minus sine of pi times 1/2. So 2 over pi, 1 minus 0, plus negative 2 over pi, 0 minus 1, 2 over pi, plus a negative, plus another positive 2 over pi, 4 over pi.